All right, welcome back. So this is our last topic in Unit 1, the idea of continuity. So continuity at a point, so we have two different definitions of continuity. It's an interior point inside the graph. A function is continuous at an interior point of C, of its domain, if the limit as x approaches C of f of x equal to the value of f of C. So this is where we had talked about plenty of times with our graphs where the limit did exist at a point despite there being a hole and there was a point somewhere else that didn't match up then. So it would not be continuous. Whereas if it just kind of went about its way, the point was filled in exactly, then it would be a continuous location. Now, an exterior point, this is important because sometimes the graph does not just go off to infinity, positive or negative directions. Sometimes it starts at 10 or 8 or whatever. So a function is continuous at a left endpoint A or a right endpoint B is that the limit as x approaches A of f of x equal to the value of f of A. Or limit as x approaches B from the left of f of x equal to the value of f of B. So the idea is it can't start or end at a hole or a vertical asymptote, I guess. It has to have an actual distinct point there, then it would be continuous on the left or right sides. So there's four types of discontinuities that we'll discuss. Really only three, as we'll discuss there with that oscillating one. But if there's a hole, it's called removable. So it's a removable discontinuity because it's easily, quote-unquote, fixed. You just fill in the hole and that's it. No longer it's discontinuous. But then we have three non-removable discontinuities where it's impossible to fix it. The jump discontinuity occurs with a piecewise function where there's a gap in the graph. You have to, that's where you have, again, your graphs will look like this. You got your line going there and the line going here. There's that gap occurring. You can't fix that. The only way to fix that is to draw a vertical line, which makes it not a function. So we can't fix the gap in the problem there. So that's a non-removable jump discontinuity. The infinite discontinuity is called, that occurs with a vertical asymptote. Again, impossible to fix. Even if I could draw a vertical line through the vertical asymptote, the graph would still never actually touch that vertical line, so it would still be, again, impossible to fix that scenario. So, vertical asymptote, infinite discontinuity. It's also sometimes called an essential discontinuity. I'm not a big fan of that terminology. It's, to me, doesn't really sound very, doesn't sound very descriptive. So I like infinite better because it's going off to infinity. And the last one's an oscillating discontinuity. This is going to occur when you're dealing with a trig function like sine or cosine, where the angle is 1 over x and x is approaching 0. You'll see that if you kind of graph it on your calculator and you kind of zoom in, it's going to be oscillating it's going to be kind of just doing something like this. So it's kind of going, it's its usual waveform. The wave's getting closer together. When we get to 0, it just kind of does something like that before oscillating more and more out there. So we have no idea what's really happening at 0 because of that. So we can't, we don't know what it is. So it's discontinuous at the location. Now, for the most part, we're not really going to deal with the oscillating discontinuity because, like I was saying there in the earlier, we only really deal with the removable one and the jump and infinite, mainly because oscillating only occurs at those two special times. Sine of 1 over x, cosine 1 over x, it's kind of impossible to occur anywhere else. Whereas holes, jumps, and vertical asymptotes occur everywhere for a lot of different functions, so that's a little bit easier to kind of explore. So there's two ways you'll see this. Either you'll be given a function or you'll be given a graph. Now, if you're given a function doing your different algebraic operations to try and identify stuff, so rational functions, I would factor. And I would see that, I have an x minus 1 that cancels, and an x minus 3 that's left over. So this would tell me the x minus 1 that cancels, the term that cancels is a hole. So I would have a removable discontinuity at x equals 1, the factor that cancels. Whereas I would have an infinite non-removable discontinuity. Apologize for the handwriting. It's awful. So an infinite non-removable discontinuity at x equals 3. You do need to specify the type of non-removable discontinuity because it either could be infinite, jump, or oscillating. So you do need to specify that. The hole is the only removable discontinuity, so we don't need to specify there. We can just say it's a removable discontinuity, and that's it. So with irrational functions, you pretty much only have those two options: remove or infinite non-removables, wholes or vertical asymptotes. Those are the only things that typically with most rational functions. Technically, you could have a jump discontinuity if you're dealing with something like this, like an absolute value scenario. Because technically the absolute value is a piecewise function, and that's where you typically get your jump discontinuities from piecewise functions. So that's what would kind of occur there. If we look at the piecewise function, the idea is very straightforward. We're looking at what's happening at the point of transition. Because individually, those two quadratics are continuous. There's nothing wrong with the quadratic equation, and everything's okay with that. So we look at what's happening from the left side. So we'd have the negative of negative 2 squared plus 2 times negative 2 plus 3. We get negative 4 minus 4 plus 3, negative 8 plus 3, we get a negative 5. So on the right side, we would have 2 times negative 2 squared plus a negative 2 minus 3. So we get 8 minus 2 minus 3, 6 minus 3, which is 3. So those are not the same thing. So therefore, we would say this is a non-removable jump discontinuity at x equals negative 2. Now, where you need to be very, very careful is not all piecewise functions, even if left and right side or the two different parts are not the same, would be a non-removable jump. You have to pay attention to what this is saying right here. Because if I have this scenario, let me just kind of make up the problem right now. If I had f of x is equal to, let's just simply say 2x plus 1 when x is equal to 3, and then x squared when x is not equal to 3, that's a situation where there's a hole there. Because it's saying is that it's the graph of x squared everywhere else except at this one spot. This one spot, it's going to be this different value. So at 3, you'd have your 2 times 3 plus 1, 6 plus 1, which is 7, versus 3 squared, which is 9. This would be a hole, so this would just simply be removable discontinuity at x equals 3. All right, so you do need to watch out for the piecewise functions. If it's inequalities there, that's going to be typically talking about a jump discontinuity if the values are different. Now, if the values are the same, then this thing is continuous. If it's going to be an equals and not equals, that could be a removable discontinuity, again, if the values are different. So just watch out for those two different scenarios. Now, if you have a graph, it's a little bit easier to identify from the graph. We can see that we clearly have holes at 3 and 10. So we would have removable discontinuities at x equals 3 and 10. And we've got that jump, that gap at 7. So we'd have a non-removable jump discontinuity. My handwriting generally isn't even this bad, but since I'm writing with a pen on an iPad screen, it's even worse. So it's kind of tough. But either way, removable discontinuity, listen to my words, don't focus too much on the writing, at 3 and 10. Non-removable jump discontinuity at 7. Now, a lot of you might be thinking, well, wait a minute. It's a hole there. It's an open circle. How is that not a removable discontinuity? Well, it's part of a jump gap in the function. That's how you know. If there's an actual full-on function coming before it, and then it's its own separate function coming after it, that's going to be a jump. There's that gap there. Whereas at 10, that's not considered a jump, because if you were to remove the hole, the line is the same line as you go through it. If this just simply has a dot above it, that is just simply a hole. Kind of like how at 3, just the line is connected on both sides of it, that means it's a hole in the graph. Whereas at 7, it's only connected on the right side, the left side's connected to something completely different. That's our jump. So then the last thing we'll want to take a look at besides the graph is you might be asked to, well, what could make it continuous? Find the value of k. Sometimes it's a or b or q or whatever variable they want. It's typically not x. Find the value of k in this case that makes the function continuous. Well, it's a piecewise function. It's got a quadratic part for the less than or equal to 3 part. It's a linear because k is a number for the greater than 3 part. By themselves, they're both continuous. So the piecewise function is only continuous if the two parts are equal. So we would say x squared plus 2 equals 6x plus k. And then we'd fill in this value right here for x. So it'd be 3 squared plus 2 equals 6 times 3 plus k. We get 9 plus 2 equals 18 plus k, 11, and then k is negative 7. Now, the problem can get a little more complicated than that. It could create, maybe there's multiple k's, so you got to combine like terms. Maybe there's a k squared, so you got to solve a quadratic. Or again, maybe it's a different letter. It doesn't really matter. The key is, if I want to make a piecewise function continuous, I need both parts to equal each other. So I would set the top part equal to the bottom part. I would then substitute the point of transition in for x, and then rearrange and solve that for the variable that they want, whether it's k or some other letter. All right, so that's it for Unit 1. That's it for our limits. It's not technically it for our limits, though. Everything we really do will be based off the limit idea, even if we're not necessarily doing limits in future topics. We'll still do in the beginning of Unit 2 with the concept of the derivative, and it'll show up at different other points. We're going to talk about applications of derivatives in Unit 4, and we get into stuff with the antiderivatives and integrals in Unit 6, and then we get into the idea of series, infinite series in Unit 10. So there's still plenty of areas for limits to be discussed, but we're not going to formally discuss it like this going forward. All right, so as always, thank you for watching, and I'll see you next time for Unit 2.